Hi, everyone. We're continuing and finishing with 3.1 on exponential functions. So here, a key application with money, compound interest, the idea that interest can be paid on interest. So let's consider a banking account with compound interest, where P is the principal deposited in dollars. That's the amount of money that you put in the bank or that you borrow in a loan. R is the annual interest rate, but in decimal form. So for example, if it's 6%, you want to use 0.06, not 6 in the formula. N is the number of compoundings, that is the number of times interest is paid per year. So for example, for annual compounding, N is 1. For quarterly compounding, N is 4. For monthly compounding, N is 12, and so forth. T is the time elapsed in years since the deposit. Okay, I'm assuming that we're operating in terms of years here, like the annual interest rate. All these must be positive in value. So, good news and bad news. The bad news is that the formula looks like this. The amount of money you have after T years, assuming that you haven't withdrawn anything or deposited anything more, and assuming the interest rate stays the same. Of course, that's not guaranteed in real life. But there's the formula for compound interest. The amount of money you have after T years, or T years after the deposit, is P, the principal, times this thing over here. Now, you might be going, what does this have to do with exponential functions? Well, this is of the form of that basic model. F of t equals a times b to the t. This is horrible, sorry. Maybe I should type this. Okay, it's of the form a times b to the t. That's a little bit better. Okay, because the deal is that actually this is of the form a number times something to the t. So this is exponential in t. Now again, the bad news is it looks like this. The good news is that on an exam, I would never have people memorize this. Okay, now in case you want a brief explanation as to why it's exponential, I think I do have it somewhere here. No. Okay. So the reason why it's exponential is that this here, 1 plus r over n all to the n, got to be careful there, all right? So this is of the form a times b to the t, where b is this guy in here. All right, so this is exponential. Okay. As opposed to simple interest, where that's just the principal plus, and then the amount of time times the interest rate times the principal. That's linear in t. That's if interest is applied to the principal, but not on any further interest. That's linear in t. Okay, so example. We initially deposit $10,000 because we found it under our couch cushion. We deposit $10,000 in an account that earns 6% annual interest compounded monthly. Monthly, that means n equals 12. You should know that. How much money will be in the account after 5 years? That is exactly 5 years after the deposit, and I'm assuming that things are happening right after the moment you get the interest. Because technically we're talking about dots. We're technically talking about geometric sequences here, but we're smoothing them out. And we're also assuming that no withdrawals or deposits are made in the meantime. Okay, so the deposit is $10,000. That's P over here. Well, do that. That's P over here. All right. The interest rate is 6%. Remember, that's got to be converted to a decimal, 0.06. 5 years, 5 years. If this were in months, you would convert to years because we're talking annual interest. All right, we use the handy dandy formula. All right, but there's a warning that I have to give you folks. And I think I'll show this to you in Word. Let's show it in Word. Okay, so what if we have something like this? Okay, let's say that we have 2 to the 3 times 4. I should write it like this. 2 to the 3 times 4. Type it in like this. And then I'll superscript it. All right. Let's say that I owe you this in American dollars. Okay. Okay. Now, what is this in reality? Well, it's going to be 2 to the 12th, because 3 times 4 is 12. Let's superscript that. 2 to the 12th, which is $4,096. Okay, 2 to the 12th is 4,096. Remember that 2 to the 10th was 1,024? Remember that from the chessboard? So that's the check on square number 12. It's $4,096, a hefty paycheck. So on your calculator, if you put 2 exponentiation 3 times 4 equals, would that give you 4,096? Try it. I dare you. Try it. No, it doesn't. Because what comes first? What comes first is this. 2 to the 3rd is 8. And 8 times 4, that's a measly $32. Not that I would spit on $32, but it's not $4,000, right? So clearly, there's a big deal here, a big difference. Now, what should you do on your calculator? Maybe use grouping symbols? Grouping symbols are so important. Grouping symbols around the 3 times 4, and that'll get you 2 to the 12th or the 4,096. Or perhaps more easily, you can figure out that 3 times 4 is 12 and just figure out 2 to the 12th. That's probably more straightforward. But in any case, you have to make sure that you're processing this correctly. And I must say that when I was a TA at UCSD, this was perhaps the most common error I saw students make on their graphing calculators. Anyway, going back to here, all right, the exponent is n times t. Okay, we're plugging in, right? P is 10,000. 1, we need the 1 there because when interest is applied, you keep what you have so far. The bank doesn't take all that money. Otherwise, that's a total ripoff. Okay, that was kind of like what I talked about before with Norma investing in stocks, right? The base or multiplier was 1.08, not 0.08. Likewise, here it's 1 plus r is 0.06 over n is 12, and then the exponent is 12 times 5. That's 60. So you might want to process that first. Okay, work it through. About $13,488.50. Okay. In fact, I'm going to do this. And this is going to stay on the screen. 13,000. Whoops. 400. Well, you know what? Let's type it. Let's type it. All right. $13,488.50. All right. And we're going to compare that with another scheme later on. Anyway, so after 5 years, after that interest is paid, exactly 5 years after you deposited your money, and you deposit your money right after a compounding period, $13,488.50. So you've made a profit of over $3,000 over your $10,000 principal. Pretty good. Very good. Okay. So now, moving on. See, this is going to be a ghost that we're going to compare to over here. Right? Continuous compound interest. What happens if we let n approach infinity? So remember, annual compounding, n equals 1. Quarterly compounding, n equals 4. Monthly compounding, n equals 12. Now, what if we go on? What if we have compounding once every day, daily, every hour, every minute, every second. Now remember how the formula worked. The idea was that if you had more compounding periods, then the interest rate was basically broken up among the n compounding periods. So if you let n approach infinity, it doesn't necessarily mean you make infinitely many dollars because you're getting a smaller and smaller piece each time. All right, so P is the principal still, R is the annual interest rate as a decimal, T is the time elapsed in years, but no talk of n because we're letting n approach infinity. We're going to implement that. And when that happens, well, good news, bad news. Good news is we get a much more beautiful formula. The amount you have after t years, and it's continuous compounding, so we don't even have to talk about when is it relative to an interest payment. A equals PE to the RT. Good news is it's beautiful. The bad news is I would have people memorize this. Pert. It's basically Pert in dollars. Now, the reason why we get that, and you don't have to know this, it's from a proof. So there's a proof in my notes that explains how when you take this thing and you let n approach infinity, then you end up with that. Now, this may recall something I'd brought up earlier. It was a definition for E. Remember this? E, that was the definition we had for E, and we're actively implementing that in the proof. So in case you're wondering why the E turns up, it's because of this thing over here. All right, Pert. So let's apply Pert. So everything else is going to be the same, except here we're going to talk about compounding continuously, as opposed to monthly, like before. So once again, we initially deposit $10,000 from under our couch cushion. We deposit it in an account that earns 6% annual interest compounded continuously. Remember, this was our result from compounding monthly, and we're going to compare. How much money will be in the account after 5 years if no further withdrawals or deposits are made in the meantime? Will we get infinitely many dollars? Remember, I said the answer was no. It's not infinity. But is it much more than this? How much better is continuous compounding compared to monthly compounding? All right, well, again, P is $10,000, R is 0.06, T is 5 years. Plug these things in. Watch out, 0.06 times 5, you may want to process that first. You get 0.3, and then your calculator goes straight through, and we get, now we're comparing to this now, we get 13,000, it's like the price is right, $13,498.59. The difference is $10.09. That's a DVD or something, right? So continuous compounding does not do us that much more favor than monthly compounding, actually. Even though we're doing something like every month, every day, every minute, every second. Well, yeah, but the interest rate's being broken up more and more also. In fact, if you were to compare it over a long time frame, I did this on Mathematica, all right, comparing monthly compounding versus continuous, all right, even over a time span of 450 years or so, about 450 years, comparing monthly compounding in purple versus continuous compounding in brown, not that much of a difference. Okay, enormous scale here, but relatively speaking, not much of a difference. You can barely tell the difference. So continuous compounding, although it is the best of the various schemes, annually, quarterly, monthly, continuous is the best. Well, you don't get infinitely many dollars. It's the best, but there's a limiting factor. E gives us a limiting factor. All right, so that's section 3.1. Next up, section 3.2, log functions, the inverses.